Yeah, this work is joint work with Duke University, University of Twente, and the University of Maryland. So before starting, unfortunately, I tested the slide in the projector and the black background doesn't look good. So what I'm going to do is gonna invert color. So there will be some weird color, but that's what it is. So yeah, sorry about the Chrome logo. So this talk is about DNSSEC, which is a security extension to DNS. So many of you are familiar with DNS, but let me give you a little background. DNS is like a yellow pages in the internet. So it translates human readable names, google.com, to translate IP addresses. So in practice, in the browsers, when you type a domain in your browsers, your machine is configured to use your local DNS reserver. So it's typically a machine near you that look up DNS requests on behalf of you. So you type examples.com, then your browser sends a request to your local reserver, says who is example.com, and your reserver will figure that out. The way it figures that out is using examples authoritative DNS servers. And it sends a response back to the reserver and forward it to the browser. But there is a security problem in DNS. So DNS has no security feature. The record could be spoofed. So bad guy can hijack the responses, then the browsers will see the different content. So as you can see, DNS reserver look up the name on behalf of the users, and the answer is coming from the authoritative DNS server. So let's focus on these two entities. And let's see how DNSSEC protect DNS records from being forged. So DNSSEC solved this security issue by deploying public key infrastructure to provide integrity, authenticity of DNS record. So DNS servers now maintains private and public key pair. So you send a request and you say that I'd like to have some DNS record by specifying DNSSEC OK bit, DO bit. So then the authoritative servers returns a record with the signatures that is signed by its private key. Now, of course, the problem is how do you validate the signatures? You need a DNS key. So it returns the DNS key. Then another problem happens. How can a reserver believe that DNS key actually belongs to examples.com? To provide authenticity of DNS key, DNSSEC mirrors existing hierarchy. Now you can see that .com zones have DNS key, and also root zone has DNS key. So now .com zones also has a DNS key and signs the DNS key record of the examples.com, and similarly, root zones signs the .com zones. So you can see is what you can see is chain of trust. So root signs the .com signs the examples.com, and the example key signs a record. So now let's see how this actually works in practice. To understand how DNS works, you need to understand just two features, DS record and the two kinds of DNS key. These two features are what DNSSEC looks complicated, so brace yourself. So as the signing process between .com and the examples.com, and also these two .com and root zone is almost the same, so let's focus on these two. So if I want to make my key example.com key sign, I create a record called DS record, which is basically hash of DNS key, and upload it to the .com zone. This process needs a kind of separate channel, so I generate DS record and go to the register website and upload it or just send it by email. So and then if a reserver want to verify the DNS key, then it simply fetches DS record from the parent zone and compare them with the hash of DNS key. And of course, this DS record is signed by its DNS key. This process is exactly the same between the .com and .root zone. And second one is two DNS keys. Each zone in DNSSEC typically has two public-private key pairs. One is called key signing key, which is used to generate the signatures for only DNS key. And the second one is zone signing key, is used to generate the other signatures. So common practice is that key signing key is stronger and longer lived. And the DS record that is uploaded to the .com is actually a hash of key signing key. So here's a summary. There are three essential elements in DNSSEC: signatures, DNS key, and the DS record. One of the characteristics of a DS record, as I said before, is it has to be uploaded to the parent John. This is the important things. And also, reservers need to verify all the signatures along the chain of trust. And also, DNSSEC can only function correctly when all principals, including servers, authoritative servers, and the reservers work correctly. So it's almost 20 years since DNSSEC is deployed, but we still don't know whether it is deployed or it is correctly deployed or not. So our question is, how's the DNSSEC PKI ecosystem manage it? So to really understand this question, we need to have a kind of longitudinal data set and covers large number of domains. And also we need to consider all these different players, servers, reservers. As one single entity doesn't do the right things, DNS doesn't work. So we collected this data set, and most importantly, we are going to publicize this data set. So here's the outline of this talk. First, we're going to look how DNSSEC are deployed on the server side. And next, we'll see the management. For those who deployed, how do they manage DNSSEC? And next, we'll see reserver and see how they use DNSSEC. Let's first look at the deployment. So if you want to deploy DNSSEC correctly, there are some steps. So first, absolutely, you have to have DNS key. And using DNS key, you have to generate the signatures. And next, this signature must be valid. So it should be the expired, and also it is cryptographically correctly signed. And also, most importantly, you have to generate the DS record and upload it to the parent John. And this record must be valid, which means hash version of DNS key and DS record should be matched. So question and the answer for this section is, how many domains are doing these all steps? So now to do that, we need the data. So we need the large scales and the historical data to see the trends. So we measured all .com, .org, .net second-level domains using Open Internet platform every day. So number of domains we cover are up to 150 million, and we regularly fetch all the DNS records and the DNSSEC records. So this is a huge data set, 147 million every single day, about 50 billion DNS records. This is previous view of DNS ecosystem. So first question is, how many domains support DNSSEC? So y-axis shows the percentage of domains with DNS key record, which means that it tries to support DNSSEC by deploying DNS key. So as you somewhat expected, the deployment is rare, by showing that only 1% of domains has a DNS key record. But the bright side is increasing. There is two ways to look at this. The glass is either 99% empty or 1% full. Yeah. The next question is, are they correctly deployed? So now we first see whether domains with DNS key provide these signatures. So y-axis now it shows the percentage of domains missing signatures. So first, in our snapshot, in our listen snapshot, signature is rarely missing by showing only 0.3% of signatures are missing. But up until recently, in November 2016, up to 2% of signatures are missing. This huge drop is due to Domain Monster, one hosting providers. They provide authoritative DNS server for their users, but somehow they forgot to just sign in. So this shows that a single entity plays a huge role in DNSSEC, but which we will see the details in a few moments. So signatures are rarely missing today by showing only 0.3% of signatures are missing. Then how about this validity? Now, so y-axis shows the percentage of domains, specific failure reasons. So there are two representative failure reasons of incorrect signatures. The first one is expired, and second one is just invalid, cryptographically invalid. So one observation is that the most of the reason are expiration, but in our listen snapshot, it seems to be managed very well by showing that only 0.5% of signatures are invalid. Then how about the TS record? So y-axis now, it shows the number of percentage of domains missing TS record. Surprisingly, 30% of domains with DNS key, they do not upload DNS record. What it means that client cannot validate the chain of trust, even though domain support tries to provide signatures DNS key, but there is no chain leading back to the root. We'll see why this happens in just a few moments. Then how about this correct news? Y-axis shows percentage of domains that has DS record but not matched with this DNS key. So it's similar. Once DS record is generated, it is managed very well by showing that only 0.2% of DS record is not matched with each DNS key. So let's see why DS record is missing. To understand this answer, you need to understand how DNSSEC is often deployed. Let's say you bought a domain from GoDaddy. You basically have two options. You can run your own authoritative servers. You set a machine, install the bind or whatever, and run it. In terms of DNSSEC, what this means is that you have to go GoDaddy and upload the DS record by yourself. Or second choice is you pay someone to run your DNS servers. Typically, it is managed by hosting providers, and they run a name servers for many, many domains, as they have lots of customers. This is called hosted DNS. Let's see how these popular DNS servers manage DNSSEC. So let's look at the most popular DNS servers by grouping the domains by name servers. We found that most of them are hosting providers, default DNS servers, and these top 15 DNS servers covers about 88% of all domains with DNS key. Third column shows the number of domains with DNS key, and second column shows number of the domains with DS record. So in ideal cases, these two numbers should be similar or same. So here's the result. What you see is we observed two classes that do right all the time or do wrong all the time. So actually, we contacted all four of these operators to ask the reason behind this phenomena. One of the administrators said that most people do not understand DNS. So imagine the white faces when I mentioned DNSSEC. I don't think DNSSEC has priority anymore currently in our organization or our customer bases. But the funny part is that they tried to support DNSSEC by deploying DNS key, but simply forgot to upload DS record. So here is a summary. DNSSEC deployment is still rare, but increasing. And the major reason of broken DNSSEC is due to missing DS record, because signatures are not rarely missing. Signature is correct. DS record is correct, but missing DS record portion is 30%. So, plus, most of the DNS support software, such as Bind or Opening DNSSEC, they manage the keys automatically, which means that they generate the key for you and they assign the DNS key using the DNS key for you. But regardless, the process to upload DS record to the parent zone is entirely depends on the administrator. So next, we're going to see how DNSSEC is managed. So there are some good steps to deploy DNSSEC in authoritative DNS servers. First, you have to have cryptographically strong key. And second, don't reuse across multiple domains. It's like a password. So if you use the same password across multiple websites, then one is compromised, then other one is also compromised. The similar thing. And third one, it must be replaced on a regular basis. So let's see the key strength first. Y-axis, now it shows the percentage of domains with keys. As there is no standard minimum key length for DNSSEC, we have adopted NIST recommendations. So one of the example of wiki is that RSA keys with the length less than or equal to 1024 bit. So here is the result. As you can see, 90% of John signing key, 40% of key signing key are weak. But we found that evidence is that key signing key is longer than John signing key, but still 30% are weak. How about the key reusability? To see key reusing phenomena, we group the domains when they share the same domains. So in ideal cases, the graph should lie on the vertical line, x equals 1. Here is the result. Now you see that y-axis starts from 0.999, which means that about 99% of DNS key is not shared, which is good. However, you can see the long tail distribution, which means some keys reuse extensively. We found that some hosting providers We use the same DNS key for all their domains, Lupia, Binary, CD Network, Cloudflare. Due to the time limitation, we're not going to cover rollover, but we found that for our measurement period, 70% of key signing key, 45% of Johnson key is not rollover at all. So now let's our attention to the reserver side. How about the reserver? So similarly, there are some corrected deployment steps for reservers. First, you have to specify DNSSEC OK bit in the header, and also you should validate DNSSEC records. At first glance, measuring reservers seems very trivial. Let's say a DNS reserver in Comcast network, and you want to measure the reserver by just sending a query. But it won't working, as most of the reserver will respond only to the local client. So for example, Comcast DNS reserver only respond to the nodes in a Comcast network. So one way that commonly being used is put some Google advertisement network that cause the client browse the website and make a DNS request. But the problem is that you have no control over the client and it's not repeatable. If you want to test on the same nodes, you just wait until that node sees the ads. So to handle this limitation, we use Luminati. Luminati is a basically VPN proxy network. But one of the cool things is that the proxy is not the servers, but residential users around the world. We can send a HTTP request directly, which means that we can make them send a DNS request. Also, there are 20 million residential nodes installed using Luminati around the world. So we have, the cool part is that we have control over the node, so we can specify the ASN number or country code to specify the nodes. And also, it is reproducible and it scales over about 20 million nodes. So what you're interested in is local DNS resolver. So we're going to focus on measuring these local DNS resolvers. So when our testbed DNS servers receive the DNS request, we first check whether it is DOB set or not. So if it isn't, we just simply return the plain DNS responses, but it is specified, we return with the signatures. But sometimes we deliberately return the busted signatures to see if a resolver does not check the validity. We also tested the other scenarios for incorrect DNS records, for example, just missing DNS record or expired signatures or just simply missing DNS key. So we measured 55,000 resolvers from 400,000 nodes in multiple ASs. For statistical significance, we only consider those resolvers where we're able to measure at least 10 different X nodes, which leave us about 4,000 resolvers. First, we found that 82% of them, they set the DO bit, which seems really promising. Now, let's see what fraction of them actually validate the response. We call that we are sending back with the busted response. We found that 82% of them does not properly validate the responses. What that means is that 82% of resolvers take the overhead for DNS records, which is much bigger than the plain DNS records, but throw it on the ground. For example, Time Warner or Roger Cable Communication, this example, you can check out the full list of the ISP list in our paper, and the data set will be publicly available. And 12% correctly validated DNS record. Comcast, Google. We also tested using Open Resolver. So these five DNS resolvers, they set the DO bit correctly and also request all the records for correctly validating DNSSEC records. Did they do the right job? These five, even though they specify the DO bit, they do not validate the DNSSEC responses. These five, they do not set the DO bit, which means that they do not support DNSSEC. So here is a conclusion. We presented a longitudinal end-to-end study of DNS ecosystem. We found that the deployment from server side is rare, but growing. But still, 33% of them are misconfigured, and also DNS keys are not managed very well. We found that most of them are weak, and also It's not shared, but some of them shared extensively, and also it rarely updated. And DNSSEC deployment from client side is also rare. Only 12% of reservers validate the responses. So most important thing is dataset and source code for this analysis will be available in this URL. And here is some recommendation. It's not over yet. So one of the biggest problem we saw is that DS record is not properly uploaded as it requires out-of-band channel. So there are some protocols support this. For example, CDS and the child DNS key, CDNS key support automating DNSSEC delegation trust maintenance. But currently, only few registries support this. For example, .cg registry. On the reserver side, modern reservers such as Bind set the DNSSEC OK bit by default, but make sure that it actually validates. There is another option to check all the DNSSEC responses. So if you don't, you pay the penalties to download all the DNSSEC records, but do not get the benefit. And also, we found that there's a financial incentive for a registrar to deploy DNSSEC with work. For example, .se, .nl ccTLD. The percentage of domains that correctly deploy DNSSEC is about 50% because they can get a financial incentive from government. So you can check out our upcoming paper, Understanding Role of Registrar in DNSSEC Deployment, which we published at EMC 17. Thank you so much.
All right, we have plenty of time for questions. Thanks for a great talk, TJ. That was awesome. And there are mics on both sides. I'll get started while people are. Right now, we already have a question, I think.
Yes, hi there, Kevin Kane, Microsoft Research. On slide 32, you had a definition of weak keys, and you said that was up to and including 1,024 bits for RSA. Did you see any significant number of keys actually strictly smaller than 1,024 bits? Or was it pretty much all just 1024?
Yeah, we found some cases using 512, I guess, but I couldn't recall.
Can you quantify?
Yeah, I couldn't recall the exact number off the top of my head, but yeah, there is. You can check out the data set. Yeah.
Okay. And did you see any significant number of non-RSA keys? Like
yeah, sure.
DSA?
There's using DSA keys and also using elliptic curve keys. Yeah, that is used. But the major part is RSA keys.
Okay, thank you.
Yeah.
All right, I had a question. The data set where you said like only 12% correctly validate, 83% incorrectly validate the resolvers. I was curious, what's the breakdown of those 83% which don't correctly validate? Was it like what was the source of the errors? And also, maybe I got confused, but 83 and 12 is 95, and what was the remaining 5% also?
For the first question, so there are some reservers that showing inconsistent behavior. Sometimes they check their responses, sometimes they doesn't. Yeah, they don't. Yeah. What is the second question? Sorry. Okay.
Hi. So, did you by any chance look at per country breakdowns?
I'm sorry?
Did you look by country breakdowns? So, for example, in .nl you mentioned we have about 50% deployment. And it would be interesting to see if some of the deployment misconfigurations vary by country.
Yes, it's not on the paper, but we absolutely observe the phenomena. For example, as I told you before, .nl, .se, they deploy DNSSEC very widely. So the percentage of the reserver that support DNSSEC is bigger than that here. Yeah.
Yeah, that makes sense. Yeah. But any of the deployment misconfigurations, any idea?
No, we couldn't see the phenomena. Yeah.
No. Okay. Yeah. Thanks.
More questions? Do you have a sense of the impact of any bias? Because I think, at least for me, this is the first time I've seen the use of Luminati as a measurement methodology. Do you have a sense of like any bias because of that? Because I don't.
Yeah, that is true. Because the user needs to install that kind of plugin to use the Luminati services. But the bright side is that the number of the users are up to 20 million over the 190 countries. So in sense that we believe that there is no huge bias in there. Yeah.
Was there any breakdown? Like, was it? I presume it wasn't distributed evenly across the countries, but actually, let's just ask Bill for his question. He'll have a much smarter question.
Okay. Bill Cheswick, University of Pennsylvania. The Let's Encrypt folks made encryption a lot easier for web servers. Do you see some sort of similar opportunity here to do this for DNSSEC?
This is very good question. So
thank you.
So as I said before in the recommendation slide, the CDS and CDNS key that do that for you. So you need for the bootstrapping step is kind of similar to Let's Encrypt. So it's try to communicate it consistently to check whether this IP address actually belongs to the reserver, belongs to the authoritative DNS server or not. After that, using the CDS and the CDNS key record, you can change your DS record whenever you want. So it's kind of similar things.
But I'm thinking, a bunch of shell scripts and stuff to make this has been impossible to do for 20 years now to run through it all and keep it going. And I'm wondering if this could be systematized enough so that a busy system administrator could make this happen and deploy it a lot more.
Yeah. So to support that, the registry needs to support the protocol. So for now, only .cz check only support that. And also, I believe the .ca Sierra try to support it, but the other else do not support it.
Thank you.
Yeah.
All right, let's thank the speaker for an amazing talk.